Okay, so today we're going to talk about unitary operators. We finished talking about permission operators. So now we're going to talk about the second class of linear operators that will be important for quantum mechanics, and that is unitary operators. So what are unitary operators? They are operators that whose adjoint are the inverse. So usually we'll deal with operators that whose left and right inverses are the same. So unitary means the adjoint is the inverse. So when you multiply u and u dagger, you get the identity. So of course, that itself is a definition, but we need to understand what does it mean. And so that's what we're going to do for today. So the point is the following. The point is the following. So what we're going to deal with is we're going to have an old basis, and they're going to be orthonormal. So and we're going to have a new basis. The old basis I'm going to denote simply as the cats 1 to d, and that's the old basis, and the new basis I'm going to put a prime on the index. So it's going to be 1 prime, 2 prime, all the way to d prime. And so what we're going to discover is that unitary operators are really they really are machines that implement a change of basis. In particular, a change of orthonormal-basis. Okay. So what it means in particular is that if I have an old basis and I want to go to a new basis, I set it up through a unitary operator. Let's see whether this goes better. So in fact, it can go both ways, of course, but we'll do it step by step. Okay. So how do we do it in practice? So remember that a linear operator is defined by what it does, right? So what we're going to do is we're going to define what it does by simply saying that u acting on the ith old basis, so remember this is the old basis, will give me the ith basis vector in the new basis. Okay. And so in other words, if I want to go from here to here, I define it so that when I act it on this guy, I get I prime. Okay? And I claim that that will give me a unitary operator. So that's the claim. To claim this definition gives me a unitary operator. So we can check this directly, but certainly if an operator is unitary, then its matrix representation in any orthonormal frame better be unitary as well, right? So if this is true, then if I take the matrix element with respect to the old basis, for example, this is supposed to be I, so therefore I should just get Pranaka Ij. Okay, so we can check this. So we're going to check that this is satisfied. And if this is satisfied, then because we've not assumed anything about this basis, right? It's just that we're going from one orthonormal to another. Otherwise, we've not assumed anything about it. If we can check this, then we see that it is unitary. So let's do that. So from here, you see that, in fact, the matrix element of U itself, with respect to the old basis, Ij is given by Ij prime. Okay, so I've swapped this I for J, and I acted both sides with I bra. And so now I can ask the question, so this is in fact what we call U hat Ij. Right? So now we can ask the question, what happens when I do I, U, say K, U dagger, J. Okay? And I sum over K. Okay, so remember, this is the completeness. If I sum over K, this is just a completeness relation, right? But what I want to check, the reason why I want to do this is because by inserting a completeness relation, I can check, is this matrix unitary or not? Well, what is this? This is in fact given by I, according to this result over here, is going to be I, K prime. Okay, in fact, let me do it step by step. Okay, so this is in fact given this relation is I, K prime, but let me write this down as this is the complex conjugate of J, U, K. Yeah? That's the root. If you have the complex conjugate of a bra acting on a cat, you take the adjoint of the cat and change the bra to a cat. And so this guy itself is in fact the complex conjugate of K prime J. Yeah? Again, I'm just using the definition of this guy and then taking the matrix element. But now what is that? This is now the sum over I, K prime, J. Again, because I took the complex conjugate. And so this sum over K prime, remember, is with respect to the new orthonormal basis. But this is again just a completeness relation, where the completeness relation holds in any orthonormal basis. So this is now just given by Ij, which is exactly correct Ij. Okay. So just from this definition alone, that if I give you an old basis and a new basis, my definition is that the old guy is converted into the new guy. I can show that such an operator is necessarily unitary. Okay. There's another way of writing this, which is that any questions about this? Okay, so there's another way of writing this, which is that instead of writing it as analyzing it from its matrix representation, which is of course perfectly fine, that's how we usually do our calculations. We can also write it as directly in terms of the cat-bra operators. And how do you do it? You in fact just write it down as a sum. Remember, you want to go from old to new. So what you do is you write down the new basis as your cats, and then write down your old basis as the bras, and you sum over them. Okay, so if you are in d dimensions, you just sum over. Yeah. So this should not you should not be confused by this. Okay. So this is the old basis, and that's the new basis. Right. It's not the same thing. It's not. This is not the completeness relation. So the thing to do is to check that this actually does, because I just wrote it down, right? So this should in fact do what I claim it should do, right? So that's the first check. So if I add u on the old basis, let's say k, does it give me k prime? Right, that's the question. That's the question to check. So let's do that. So we add u on k. That means that that is the sum over I prime I, and then it's acting on k. But then this gives me Kronecker ik, which just means that because it's orthonormal, k, when you sum over I, the only term that is non-zero is when I is equal to k, which means this becomes simply k prime. So indeed, when I add u defined in this way, on k, it gives me k prime. So it does what we want, right? And unitarity can also be checked directly. So you take u dagger multiplied by u, and what happens is that, remember, when you take the dagger of a cat bra, it becomes, you swap the cat bra, basically. So it becomes, instead of I prime I, now you have I prime, sum over I, and then now you act it on u, so I need to give it a different label because this is a sum over I, so now I need to sum it over j. So it's j prime, j. Okay, so again, this is u dagger, this is u. This acting on this is going to give me Kronecker ij. Okay, this is the sum over j. And so I'm just going to skip ahead and say that therefore the two sums are going to be collapsed into one sum. Because again, when I sum I and j, this acting on this will tell me that the result, term by term, it will be 0 unless I equals to j. Right? And so this will just be I, and then everybody is now I. This has become a Kronecker delta, so it just becomes I. Well, this is a completeness relation, and so this is just identity. So this is at the operator level that we can verify directly that it is unitary. Okay. If you want, you can also do u dagger instead of u dagger u. Okay, and you'll find that you get the same thing. Okay, so what we've done so far is to say that u is the thing that gives me the new basis when x on the old. Now, if I just give you a, so let's turn it around, so the logic, let's turn it around a little bit. Let's say that I give you a unitary operator, okay? Then I can guarantee that when I act on an orthonormal basis, it will give me back an orthonormal basis. Okay, so this is a little bit different from what I'm saying over here. Okay, here I gave you two bases which are orthonormal, and I define U by saying that it's going to give me the old, give me the new by acting on old. But now if I turn it around and I say, here's a unitary operator. So I've already defined what it is. And I already tell you that it is unitary. Okay, so in the homework, you're going to do two simple examples of constructing a unitary operator. One of them is actually just rotations in 3 dimensions, but actually it's really in 2 dimensions, but you write it in a way that is a 3 by 3 matrix. Okay, and the other one, I gave you the transformation, and you're supposed to check that it's unitary. And you're also going to diagonalize it. Okay. So, we changed basis for graphs. We changed basis for cats. Now the question is, how do you change basis for linear operators? Okay. So what it means is, if you have a linear operator x, and you try to write it down in some old basis, you're going to try to figure out how do you go about changing it to a new basis. Okay, so the trick, as you can probably guess, is the same as we use here, which is to insert a completeness relation. So here I'm going to insert it to the left of x and to the right of x. Right? So I'm going to call it K and L. So I, K prime, X, L prime, J. Okay? And so you see that this is the matrix element of X in the old basis. And now this is the matrix element in the new basis. Okay. And again, let's remind ourselves that when you have I, K prime, this is in fact I, K prime is in fact U, right? So this is in fact just simply I, U, K because you want to transform from the old, from the new, from the old to the new, right? And that is U. And this is now L prime J. So this is in fact L J, but this is actually U dagger, right? And how do we see that? It's here. prime unprime is U dagger. So in terms of matrix elements, we can write it as X hat ij is now equals to U I K and then X hat K prime L prime and then U dagger L J. Again, I put a prime on the X because it's in the new basis, but U is computed in the old basis, so I don't put a prime on the indices. Right? So U dagger, again, there are no primes on the indices because of as computed in the old basis, and this is in the old basis. And so this is basically matrix multiplication. Right? So this is saying that X hat, meaning X in the old basis, is just U computed in the old basis multiplied by X prime, meaning X in the new basis times U dagger. And so likewise, I can, just for the cases, or for the graph, I can move the U's on the left-hand side, and I can write down the new X prime, the new X in the new basis, as U dagger multiplied by X in the old basis times U. Okay. And of course, let me just remind you, diagonalization is exactly such a process, right? Diagonalization is such a process because for Hermitian operators, the new basis is usually the basis where you're using the eigenvectors. And that's where it is diagonal. Right? If you're using the eigenbasis as your new basis, it is diagonal. But before we do that, let's in fact understand it in a more general way. If I do have, so as we have seen here, U is an operator that implements a change of basis. But I can think of it in a more abstract way as well, which is to say, if I give you a unitary operator and an arbitrary linear operator, and I'm trying to sandwich the linear operator between U and U dagger, then how are the eigensystems related between X and X sandwiched between U and U dagger? Right. And so as you may have guessed, because the meaning of U is just a change of basis, what you should discover is that the eigenvalues remain the same. The eigenvalues remain the same, but the eigenvectors are rotated. Rotated in the complex sense, I guess. Okay. So let's think about that first. So again, if I give you X and I put it between U dagger and U, and I define this new operator as X prime, then the fact is that if this is the case, then X prime and X share the same eigenvalues. Okay. And it's not difficult to see at all, because the proof is very simple. So let's say I have x, and it acts on lambda, and gives me lambda. Okay, so let's say I know all the eigenvectors and eigenvalues of x. And all I have to do is I have to insert, because u is unitary, all I have to do is I have to insert u and u dagger in between lambda, and then I multiply both sides of this equation by u dagger. Okay, so this is u dagger lambda. Okay, so remember, all I've done is, this is an identity, and I've multiplied both sides by u dagger. So what do I have here? I have u dagger x u, and this operator, which is x prime, is acting on u dagger lambda, and that is equals to lambda times u dagger lambda. Okay. So we can write it this way, right? So x prime lambda prime equals to lambda prime. So lambda, I should probably say something like cat prime, right? But let me just leave the prime as it is. So it's the same lambda, but I put a prime just to denote that this is not the same cat as before, but a rotated one. So let me just define it. Lambda prime is u dagger lambda. But so apart from the u dagger, it's the same thing. So x prime has eigenvector lambda prime, which is u dagger lambda, and eigenvalues lambda, right? So this is the vector, and this is the vector and the value. Okay, and for x, it's just given by lambda. But because there's a invertible relationship, right? If I give you this, I can give you this. If I give you that, I can give you that. So basically, they share the same spectrum in this sense. Same eigenvalues, but just rotated eigenvectors. Okay. But essentially, they're describing the same system. Because that's how you can think about it. Because U just is a change of basis. Okay. And likewise, fact number 2 is axis formation. So is x prime. And this you can check very easily is that. Okay, just take x prime dagger. What is x prime dagger? It's the dagger of u dagger x u. And remember, if you take a dagger of a product of operators, you just write it in reverse and take the dagger. So u becomes the first guy, and you take a dagger, and then x dagger, and then the dagger of u dagger. The dagger of u dagger is just u. X, remember, we have assumed is permission, and u dagger is just what it is. Right. So this is in fact, of course, x prime itself. So again, the interpretation is that under a change of basis, a change of orthonormal basis, the permission character of the operator is not changed, is not altered. Same thing for unitary operators as well. Okay, so if x is unitary, x prime is also unitary. Okay, and that we can just check again. Let's calculate x prime dagger, x prime. Right, and this is, what is this? This is now the same calculation, except that it's not permission anymore, so I'll stop at here. Okay, so this is u dagger, x dagger, u. And then x prime itself is u dagger, x, u. So u dagger is 1. And x dagger x is 1, and u is unitary. Okay, so therefore x prime dagger x prime is the identity. Again, the significance of all this is that it's telling you that when you change your basis, as long as they're orthonormal, you're not really changing the character of these operators. And I guess it's a good place to emphasize, especially for the permission character of the operator. This is a little bit like saying that physics should not be dependent on the coordinates you use. It's not exactly the same, but it's very, very similar. Just like I told you guys before, if I want to describe this room, it should not matter whether I use Cartesian coordinates or spherical coordinates, or if I rotate my axis one way or the other. It shouldn't matter, right? It might be much more difficult, practically speaking. One basis could be much more cumbersome to use than the other basis. But it should not change the room itself. The room is what it is. Right? The coordinates are a human construct that we use to help us with our analysis. But it should not otherwise change the physics involved. So there's a very similar spirit here that's going on. But so before we take a break, I just want to emphasize one more point, which is also very important. So why unitary operators are so important is not just because they implement change of basis. That's kind of actually the boring part. But because of at least two reasons. Okay. So let me. So the first reason is that of symmetry. So it turns out that a lot of quantum mechanical systems are symmetric. They enjoy, for example, rotational symmetry that we'll talk about extensively. When you do relativistic quantum mechanics, you'll find that the fundamental laws of nature are symmetric under Lorenz transformations. And you have to find a way to somehow implement these symmetries under using the language of linear algebra, right? Because that's what quantum mechanics is, which is why we spend so much time understanding linear algebra, because that is the fundamental framework which we use to describe quantum mechanics. So it turns out that whenever you have a symmetry, which means, so you can ask, what is a symmetry? A symmetry means, so let's again think about rotations, right? So a symmetry means that if I rotate my experiment, it should not change the outcome of the experiment. That's a rotational symmetry, right? So whether I orient my experimental apparatus this way, or I orient it this way, or this, for many situations, it should not change the outcome of what I'm trying to do. Same thing for Lorenz transformation. If you know some relativity, you know that in all inertial frames, when you look at physical laws, should be the same in all inertial frames. So whether you are moving 500 kilometers per second with respect to the galaxy, or if you're at rest with the galaxy, as long as you're moving at constant velocity with respect to an inertial frame, you should be in your own inertial frame, and your laws of physics should be the same. It should take the same form. And how do you express that in terms of a quantum mechanical language? It turns out that all such operations so rotations, for example, are either unitary or anti-unitary operators. In fact, the only anti-unitary operator, I hope I'll have the time to talk about it, but the only anti-unitary operator I know about is that of time reversal. If you try to reverse the direction of time in quantum mechanics, you have to apply not just a unitary operator, but you also have to take a complex conjugate, and that's where the that's where the NT comes in. But for everything else, rotation, translation, that we'll talk about very soon, all of them are implemented as unitary operators acting on your vector space. And it will turn out, as we'll see, that these unitary operators are generated by Hermitian operators. There's an intimate relation between unitary operators and Hermitian operators that I will discuss very soon, as in particular unitary operators that are continuous in some sense. And it will turn out that these Hermitian operators themselves will, because they're Hermitian, will turn out to be related to observables, things that you can, in principle, measure in the math, right? And so angular momentum is such an example. So angular momentum. So Hermitian, let me just write that down. So Hermitian operators generate continuous unitary operators. So for example, angular momentum. Is intimately related to rotation operators. Which we do, and then momentum, linear momentum. related to translations, spatial translations. Okay. And then the second important reason is because time evolution is unitary. In quantum mechanics. In fact, you will see it's in fact a unitary operator, and it's very important as unitary because we need to conserve probability. So when we get to it, we'll talk about it. But basically, if the particle, if your quantum mechanical system can be found somewhere at this moment in time, you better be able to find it somewhere else or somewhere at some later time, right? Otherwise, it means that something has gone missing, right? It cannot be that the probability of finding it somewhere is 1 right now, but 10 seconds later, the probability of finding it somewhere becomes only 90%. Then where is it? Right? Only 90%. Then where's the other 10%? Right? So quantum mechanics will break if you do that. And so that's why we want time evolution to be unitary. Any questions? All right. Let's take a 10-minute break and see you guys 2:10. Yes, go ahead.
So, is there a system of with operator X is unitary? Can you take an example?
A system where U is unitary, X is unitary.
Yeah.
What do you mean? What do you mean by that? So, for example, U, as I was saying here, U will end up being the rotation generator, rotation operator, or the translation operator, right? That's the first point here, right? So unitary operators, you're basically asking me why are unitary operators important? Is that right?
Rotation and boost is not necessary to have eigenvalue.
Rotations, yes. Not translations also. So we'll see that. We'll see that very soon, actually. Rotation and translations, we'll do it very, very soon. And we'll see that they do have you are able to diagonalize. You will be able to diagonalize all of them, and at least for the free particle and for translations for the free particles, and for the rotation operator, we'll see it repeatedly throughout quantum mechanics. Yeah. Is that your question? You basically want to know. I think your question is basically, when do unitary operators show up, right? And like you said, is exactly, we're talking about exactly because all the symmetry operations that you care about in quantum mechanics will show up as either unitary or anti-unitary operators. If it's a symmetry, it will be either one or two. It's a theorem due to Wigner, actually. I should maybe say that. It's a theorem due to Wigner. If you want, you can look this up. I've never read this proof before, but it's a very well-known result.
So do rotation operators also form a basis?
What do you mean by a basis?
Form a basis because you just write out x on lambda equal to lambda times.
Remember that was for Hermitian operators. that proof was for, was to tell you that when you change a basis, when you sandwich a permission operator between U and U dagger, that does not change the permission character of the operator. That's not the same, it's not the same thing as, I'm not saying that X is unitary, right? I think you were saying, that theorem was saying that X prime U dagger XU, if X is permission, so is X prime. That is that theorem that you were referring to, right? Okay. Yeah, so as I mentioned before, if you do have something that is diagonalizable, then the process of diagonalization is in fact implemented through a unitary operator. So let me try to find the better marker. So let's begin at the end. So suppose I can diagonalize my operator. What that means is I can write it down in terms of the in terms of the eigenbasis, right? So this is the eigenbasis. But if I usually, that's not how it works. Usually I start off in some arbitrary basis, hopefully orthonormal, but I want to get to this eigenbasis, right? So what happens then is that basically I have I need to find a change of basis. So how does it work? Let's write it down. So I insert a completeness relation on the left and on the right. Right, so now there's triple sum, right? There's a sum over the eigenvalues, and there's a sum over the I and J completeness relations. But now you might recognize that this overlap and this overlap actually refer to a change of basis. Right. So if I define U to be, let me skip to what I wrote in my notes. As I acted on, so now I is an arbitrary orthonormal basis. Orthonormal basis. Then this guy acting on the kth eigenstate. Sorry, kth orthonormal basis. I define it to give me the kth eigenstate. Then this guy would now be given by in fact the matrix element around the K I U K, and then this guy is just going to be the complex conjugate of remember this guy the K J, remember it's just a complex conjugate of J lambda K, and J lambda K is J U K, this is J, and therefore what do we have here? We have K, around the K, and then this is now K, U dagger, J, J. And so in terms of the matrix elements, matrix components, you can write this as U, I, K, and then this is now just a sum over the diagonal components of the eigenvalue matrix, and this is U dagger K J J. Okay. But what is this? This is in fact I X hat I J J. Right. This is just the matrix component of X in some arbitrary orthonormal basis. In other words, if you know this, then the diagonalization process is in fact just the search for a unitary transformation that will bring you from X to a diagonal basis. Right? So X, let me just write it down. So this should be familiar. X should just be equals to U, and then multiplied by the diagonal matrix lambda through lambda D, U dagger. And that's what this is saying. Right. This equality here is saying that if you give me X, I can compute its elements in an orthonormal basis, and the process of diagonalization is basically a change of basis from the old basis to the new orthonormal eigenbasis. Right. So let me just write it down. So diagonalization is just a process of rotating the all orthonormal basis to the eigenbasis on the plane. Good. Any questions for me? Actually, the more general statement you guys might know is that it's not always possible to diagonalize an operator, but there is something called the shear decomposition. So you can always find a change of basis that takes you from whatever representation you have for X into something that is diagonal, containing the eigenvalues, plus something that is strictly upper triangular. So 0 all the way here, 0 here. Right, so upper triangular. a more general statement, something that you may have learned before, but I'm just trying to phrase it in a different, slightly different language here, as a change of basis. Okay. So, the next thing I want to talk about is what we've talked about before, but now that we've talked about unitary transformations and also the difference between upper and lower indices, I want to talk about it again, which is that of the trace. So as we know, the trace of any linear operator, we have defined it to be the sum over the diagonal components in any orthonormal basis. So I've asked this question before, which is that I define it with respect to an orthonormal basis, but how do you know whether if you change a different orthonormal basis, how do you know that you still get the same answer? Right, so this in matrix notation is x hat I sum over I. And the point is that, as I've said before, because upper and lower indices transform oppositely, from lower indices, we will see that the trace is a genuine scalar. So i.e., what do I mean by is a genuine scalar? It means that it is independent of the basis, as long as it's orthonormal. Okay, so let's understand this statement. So suppose we choose a different basis, I prime x I prime. Okay? And what we've discovered was, previously we discovered that we know how to convert between one basis to another. If you write a linear operator, so I'm going to use that result so that I don't have to do it again. Okay, so this is x hat I prime I prime. But the prime indices, the upper index would transform as a U dagger. So it will be U dagger I, say A, X, A. And then the lower index would transform as a U. Okay, this is something we proved earlier. Okay. But this is where what I mean by opposite transform in the opposite way comes in. Right? This guy, the upper index transforms like a U dagger, the lower transforms like a U. So I can now sum over the I first. So what do I have? I have now basically U, B, I, U dagger, I, A. This is just a matrix multiplication of U dagger, U dagger, and I take the BA component. Okay. Again, because of this II, it's just the U multiplied by U dagger, and I take the BA component. So this is just the identity BA. Of course, that's just connector BA. And so what does that mean? It means that this is X, AB, connector BA, and X at AA. You sum over A and B, but it's non-zero only when A equals to B, right? And so what have we proved? We've shown that if you take the sum with respect to a prime basis, it's the same if I take any other basis. Right? So this basis is not the same as this basis. The only thing I assume is that these are orthonormal bases. And therefore, like I said, the trace is a genuine scalar. As long as you use an orthonormal basis to do the trace, you will get exactly the same answer, regardless of what basis you use. Okay. Any questions for me? So at the operator level, what you're going to show in your homework is that is the analog of what you might be familiar from matrix algebra, right? So, but this is now operators. These are now operators. So the trace of xy is the same as the trace of yx. This is certainly true for matrices, but now you're going to prove it for operators. And then the trace of U dagger x U is the same as trace of x. Okay, which again is true of matrices, but we don't prove it for operators. This is another way of saying what we just said. Right? For what I did was to just prove it directly, but this is another way of saying the same thing, which is to say that the trace is a genuine scalar. Okay. Good. No questions for me? Everyone's so quiet. Except Li Hao. No questions. Okay. So I want to talk about tensor products next. Right. So there will be so I moved a little faster than I moved a little faster than I thought. So let me do tensor products. So let me say it in words first. So the tensor product is just a way to multiply. It's just a way to formalize the multiplication of vector spaces. If you have the same vector space, but you want to make multiple copies of it, or if you have different vector spaces and you want to multiply, you want to stick them together. Those are these are the instances where you will get a tensor product. So for example, in undergraduate quantum mechanics, you have probably taken the tensor product of your wave function in position space and the spin vector. Right? So you're not told how the heck it came about, but usually at some point when you start having to deal with spin, you have to take the tensor product of maybe it's not explained in such a formal language, but essentially what you're doing is what you're doing is in fact the tensor product. So the symbol that we use is a cross with a circle in it. So let me say the following first. Okay, so suppose I have n vector spaces. So they may not be the same vector space, or they can be the same vector space. It doesn't matter. Okay, but what will happen is that I will take a vector from each of the vector space, which I will label as alpha 1, 1, alpha 2, 2, all the way to alpha n. So let me explain the notation a little bit. This label here, maybe I'll do this. Alpha I, alpha n. So let me explain the notation a little bit. This is just the the vectors from the ith vector space, and this is just a label. Okay, I had to put an I just because I don't have that many alphabets, right? So I just want to use the same alphabet and put an index on it. But sometimes it can be, remember that we often use, for example, the eigenvalue of some operator to label our state. So this can be an eigenvalue, it can be a label for the orthonormal state, whatever it is, right? But the 1, 2 through n is there because I have to tell you which vector space the vector is coming from, right? Sometimes, if the context is clear, then I don't have to do it. But otherwise I'll have to tell you explicitly which vector space is coming from. So this is one element in my giant now giant vector space. Okay, so in my notes I call it script A. And so yeah, I don't know why I use such a horrible looking anyway, so yeah, I usually use a symbol I can write, but this is hard to write. Okay, anyway, so this is an element in my giant vector space. Okay, so the question is, what are the rules of manipulating it? So here are the rules. Okay, so the first rule is that it is linear. Is distributive over addition. What is distributive over this? This is the tensor product is distributive over addition. So for example, if I have the first vector crossed with, say, alpha prime plus beta prime, and then cross with gamma, then I can just distribute it. So it's alpha cross with alpha prime, cross with gamma, plus alpha cross with beta prime, cross with gamma. Okay? So of course, if you have scalars, you can distribute over them. Actually, that's the next rule. A scalar multiplication, you can just pull them out and be factored out. Yeah, can be factored out. So what does that mean? It means that you have alpha cross with, say, some number times alpha prime, cross with alpha prime prime, and so on, then this is just the same number times